Okay, well, thanks so much for having me here. I truly enjoyed all the talks of today. Looking forward to the sort of more technical ones tomorrow. Anyway, so I would like to present you sort of with my view on localization and delocalization of charge carriers, in particular in molecular organic crystals. So these are the sort of the simplest materials that we studied to apply our sort of methods that we are developing. This okay. So probably most of you don't know me. So I'm a computational guy. So between physics and chemistry, and these are the kind of three topics that I'm currently working on. I'm interested in the nature and the transport mechanism of charge carriers in sort of soft materials. So it's not quite clear what soft is, but it's usually organic materials as well as biology. So also microbes and bacteria are very good at moving charges either to extracellular substrates or among bacterial cells. And then they're using electron transfer proteins that rival the conductivity of synthetic organic semiconductors. And the third sort of interest area is to understand what's going on at the interface between transition metal oxides and liquid water. Again, here with a focus on solar fuels. These are the kind of methods that we are developing and applying. So I'm an atomistic guy, so it's an electronic structure, so it's usually DFT, molecular dynamics, and especially mixed quantum classical non-adiabatic dynamics. So there we are leaving the electronic ground state and can also describe processes that are happening on excited states. And then if you want to go to longer time scales and length scales, then typically use master equations, kinetic Monte Carlo, Markov models, or these kind of things. All right, so I do have problems a little bit with this pointer. I'm sorry for that. So that's the content. So it's officially 50 minutes. So I try to introduce some structure in my talk here. So at the beginning, I would like to present you sort of a new, well, I shouldn't say new, maybe a novel method for simulating carrier transport in organic materials. And we gave this the sort of elegant abbreviation FOBSH because this stands for fragment orbital based surface hopping. Then I would like to present two kind of applications of this methodology, one to charge transform organic single crystals, and there I would also like to compare our results to this transient localization theory that we have heard of a lot today already. Second application is on sort of on tetracene-based columnar stacks. And at the end of my talk, I would like to discuss a little bit about these design rules that we probably should follow if we want to sort of decide new high mobility materials. And okay, so this is usually the slide that I show to sort of a non-expert audience that has never seen an organic semiconductor. So here at this place that has contributed so much here to these areas, I think I just skipped this slide here. So what I just want to say is that, I mean, these materials, they are basically, we use them in our everyday lives, but so it's interesting that we have sort of not really a very good understanding of actually what are these charge carriers and how do they move from A to B in that material. Okay, so here I just show a cartoon of sort of extreme scenarios, so you could think of that the carrier is just a localized charge hopping from one molecule to the other, or a fully delocalized, a band-like object here, so what we know from similar to inorganic materials, or maybe something in the middle, something like the wave packet, and not really localized, not really delocalized. Okay, so what I would like to explain here quickly is that the transport in organics is really in a very difficult regime because two of these traditional transport theories break down. So what do I mean with this? So the first one would be sort of localized hopping of a carrier from one molecule to the other. But this theory, I mean, all these theories, they are only valid within a certain regime, right? And these, the hopping theory really has a speed limit, okay? So the ET rate for the hopping must be much smaller than the vibrational relaxation rate of the modes that are coupling to the electron transfer, okay? And that was investigated in detail also by Alessandro a long time ago. So there is an upper speed limit, but there is also a lower speed limit set in band theory, okay? And this obviously comes from the fact that the carrier mean free path must be larger than the lattice spacing so that this theory is valid, and that gives us this lower speed limit. Now if you put in the numbers into these approximate equations, then you get something like this. Hopping model valid for mobilities, let's say smaller than a few 0.1 square centimeters per volt per second, and band theory is usually valid for mobilities larger than a couple of 10 square centimeters per volt per second. And so you can see this already. So most of the organic semiconductors, the good ones, they are somewhere here in between, for which there has not been a good theory, well, at least until 2011, when for the first time this transient localization theory came up. Okay, so so there, if you're a chemist, you think in different terms. So this is the alternative picture that I would like to present here. So there's also something that's called electron transfer and Marcus theory in chemistry, and that's usually happening here between two iron atoms, for instance, in high dielectric media like aqueous solutions. Now in these high dielectric media here give rise to high trapping energies, okay? So that means that it's energetically much more favorable that the electron localizes just on one iron and is not delocalized over both. And this is because this, in chemistry departments you would say reorganization energies. In material science departments you would say trapping energy. So this is this lambda, which is basically the curvature of that well, is orders of magnitude larger than the electronic coupling between these two iron atoms. So this is typically 3 orders of magnitude in aqueous solution. So you have the charged states are nicely localized. And in order for the electron to go from here to there, you have to go to that point here where the states cross. And this takes a lot of energy, and therefore these states, they are happening on the millisecond time, so very slow. Now, in organic materials, the situation is very different, because you have obviously here not 78 anymore, but you have roughly 4 or 5. So low dielectric. So that means that reionization energy is much smaller, typically 100, as we have seen, 100 or 200 millieV. And at the same time, the electronic coupling between the molecules is much larger. So in this scenario here, lambda and HB, they are on the same order of magnitude, and therefore the charges are no longer localized on the single molecules. Okay, so this is sort of the chemistry interpretation of that. So then the question is, of course, what to do next. So recent progress, well, recent 2011, still sort of recent, has been made in terms of theory, transient localization theory. I'm not going too much into the details of this theory. If you want to do that, please consult the literature here. And also, Henning Searinghouse talk was much about this theory. And I would, so what we have developed over the last couple of years is not transient localization theory. Which is not,
sorry, but it does say it's about shutdown.
Oh no,
batteries, so.
I can do. Oh, sorry. This is the tricky bit here in the UK, where you have to press that button. Right? I think that. Thank you very much. Well, let's see. Because in previous, well, I'm very grateful that previous speakers have mentioned this thing, but it has really nothing to do with transient localization theory. So transient localization theory is a very, very nice theory. It's beautiful. It basically, at the end of the day, you get a very nice formula. But it does have lots of approximations in there. Okay. especially with regard to the electronic dynamics, because actually you don't really solve for the electronic dynamics here. So now in this method that I would like to present here, what we are doing, we are really looking at the time-dependent electronic Schrodinger equation and solve that under the influence of classical nuclear motion. And so this is goes, I would say, in many respects beyond that theory. Of course, the disadvantage is that this is numerical. Okay, at the end of the day, we don't have a nice equation to insert into, so we really have to simulate that, propagate that on a high-performance computer. And these are the references, the papers that we have published so far on that methodology, at a rate of 1 paper a year. So this is sort of acceptable, I would say. So this is. This is in a very simple cartoon, this is what we want to do. Our aim, simulating charge to carry nuclear dynamics in organic materials from first principle, quote, because we are not doing first principle in terms of electronic structure, but in terms of, not even at dynamics, but what we are trying to do, and what previous speakers have also stressed, is that in organic semiconductor, what is very important is not only electronic dynamics, but especially how the electronic dynamics is coupled to the nuclear dynamics. So the electron dynamics affects the nuclear dynamics, but there is also a back reaction. The nuclear dynamics affects the electron dynamics. So you have to solve both problems at the same time. And I think this is probably what sets it probably slightly a little bit apart from the localization landscape, as far as I could see, because I didn't see a time-dependent electronic Hamiltonian in there, but maybe we can discuss this later. So this is I'm just looking at a very simple problem. You just have the semiconductor, you are removing an electron here somewhere, and then I would like to understand what's happening to that charge in time, okay? And obviously, since we don't have light or anything else, so it will just sort of propagate within that valence band. Or the other question would be what's happening to the excess electron if you inject that in the conduction band. Okay, so lots of sort of preliminary slides. Now, in order to do that, solving electron-nuclear equation, sort of exactly, there are also many methods available, especially in the theoretical chemistry community, and it's a real zoo of methods, and you can compare it with sort of Jacob's ladder a little bit. I don't know, you probably know Jacob's ladder in the end, so that's the ladder that brings us from earth to heaven, or from heaven to earth. So this would be essentially the heaven for us here, okay? A multi-configurational time-dependent Haar tree. So this is a very rigorous method, but the problem is you can only apply it to relatively small systems, and then there are these other systems here. So at the bottom of that is Ehrenfest dynamics, which probably most of you is familiar. But the kind of dynamics that I do here is fused switch surface hopping, which has been shown to be a good compromise between accuracy and computational efficiency. At the end of the day, I would like to apply this to a real material, so I cannot, I cannot start with a method that's here at the very top. All right, so surface hopping, I will explain what it is. Has been already implemented in many electronic structure codes using time-dependent density function theory to get excited state energies and gradients. Typically, 100 atoms, 10 femtoseconds. Not very good for the systems that we would like to study. So we have to, so the question is how do we get bigger and simulate for longer? So obviously, since we're in Cambridge, I have to do this up here, even though we are not at St. John's, but still. So I'm very grateful now to Dirac, of course, for this sentence here. It therefore becomes desirable that approximate practical methods of applied quantum mechanics should be developed, which can lead to an explanation of the main features of complex atomic systems. And so this is what we're doing here in this method. So what I would like to first explain before I present some results is the major approximations that we make. So the first one is that the exact electron-nuclear quantum dynamics is replaced by mixed quantum classical dynamics. So that means we are not treating electrons and nuclei quantum mechanically. Instead, we only treat the electrons quantum mechanically and the nuclei classically. Okay, so that's good. So you can doubt that this is a good approximation, but usually it is, especially if your modes are not too high frequency and at room temperature. So this usually would have its problems if you go to very low temperatures, but this is not our aim. The second approximation is that concerns the electronic structure. The time-dependent multi-determinantal electronic wave function is replaced by a one-particle wave function describing the excess electron or excess hole. So what we are doing here is that the correlation between the electrons, which is a very tough problem in quantum chemistry, we don't treat that explicitly, but only implicitly. So there are also no explicit co-electron or valence electrons, so their effect is implicitly included in the parametrization of the electronic Hamiltonian. So that's the method in a nutshell. So this is what we're doing for the excess charge carrier, electron or hole. So what we're doing, we are expanding the excess charge carrier in a basis of HOMO or LUMO orbitals, HOMO for the hole and LUMO for the electron. So our charge carrier wave function is written here. So it has a spatial dependence, just r, and this is time. And this is just a linear combination of our HOMO or LUMO orbitals of the isolated molecules. And now it's important to realize here that this depends on the dimensions, 3D, and also on the nuclear positions, all the nuclear positions of our system, which in turn depend on time. Okay. Now, if you insert this into the time-dependent Schrodinger equation, then you just get the usual equation for the time population of the expansion coefficients here. And on the right-hand side is just the electronic Hamiltonian matrix elements. And important, this is a quantity that we haven't seen before here. These are the non-adiabatic coupling elements. So this basically tells us how much nuclear motion couples to the electronic transitions between different electronic states. So this is what we propagate in time, and that this will give us the time-dependent hole or excess electron wave function. And remember, I told you, so we have to couple this to the nuclear motion. And the nuclear motion, since we treat them classically, is nothing else than Newton dynamics with the forces derived from the eigenenergies of that Hamiltonian here. Okay, from the but this is not all, because I mean we have to allow that our nuclei not only move on the ground state but also on the whole manifold of electronic state, including the excited state. So this we incorporate in the surface hopping methodology by stochastic hopping between these potential energy surfaces with a given hopping probability that was derived by, well, cannot really be derived, but suggested by John in 1990. Okay, so a little bit more detail. I hope it's not too boring, but I thought since some of you are computational people, it might be interesting how we actually do that. So how we construct this electronic Hamiltonian. So now during IMD, this thing has to be created many hundred millions of times, okay, within 24 hours. So we need to have efficient methods to calculate the electronic, the matrix elements of this Hamiltonian. Now if we do the off-diagonal, so these are the electronic couplings that we've seen before, we do that with a very efficient analytic overlap method. I have no time to go into the details here. And the site energy, so that's the energy when a given charge carrier is on a given site I. We calculate this with the force field. Okay, and this is, if you think it's a sort of a kind of tight binding Hamiltonian that we use here. But the elements here, they really come from real electronic structure calculations. Okay, so these are the energies, but then since we do dynamics, there is a force that's acting on each nucleus of our sample. So how do we calculate that force? So this is the kind of sort of strategy here. So what we have to do, since we are working here in this site-localized basis, we need to take the gradient of that electronic Hamiltonian that I've just presented before, and then we have to do nothing else than do a sort of a unitary transformation of that. And this unitary transformation matrix transforms from the diabatic or site-localized basis to the adiabatic or eigenstate basis. Okay, and this gives us then the nuclear force on a given excited state energy with index I. And the non-adiabatic coupling vectors you can get in a similar way as the forces, and you have some additional terms that probably would extend up to here, but the terms going from here to there, they are unimportant. So that's nice. And actually, to make the dynamics work, you have to do a couple of other things, and so David knows very well about these things. So you have to put some decoherence into the electronic dynamics. So this is a little bit of a problem in surface hopping, but you can do this relatively rigorously here. So these things have been worked out by, again, Kretz, Dorowski, Bittner a long time ago. So this is some decoherence correction that we have. And there is also a problem, since we have many states, we have this band, so we have lots of different electronic states, and the spacing is very small. It's very easy to actually get on the wrong surface in the end. So you have lots of surface crossings, and we have implemented a state tracking algorithm that takes care of them. And then there is also another technicality. We saw when you do these things for the first time, you see kind of strange things that happen. That's due to that decoherence correction, so we also have to remove these things. So there are three things that we have to do in order to make the normal surface hopping algorithm work. Okay, so let me then come to the applications. So now we have this methodology. So how do we best, let's say, validate or benchmark it? And then I was actually surprised that there are actually quite only few very well-defined sort of organic crystals where you have both the crystal structure and a pretty good hard value for the experimental mobility. Ideally from time of flight measurements, where you really probe sort of the bulk mobility. But I think, well, at least I think pentacene is still not so clear, and rubrane is not so clear. But for these, at least, you have pretty sort of robust experimental numbers for TOF mobility. So this, I thought these are good candidates. And again, these are basically materials that form these herringbone layers. So you have conductivity in that plane and zero conductivity orthogonal to it. Okay, now so previously I think Jenny said it would be nice to show a movie of a polaron. Well, this is sort of the movie of a polaron in this material PMSB. Now this is it all working? No, is it? Yeah. So this is the material that has the lowest mobility of the 8 that we have investigated. And so what you can see, you start with a localized polaron, and then every now and then it sort of delocalizes, and then relocalizes on another site. Okay. And this is what I would classify as sort of small polaron hopping, even though you see that the carrier is a little bit spread. But most of the time, it's basically localized on a single molecule. And this you can already see from the parameters that you get from electronic structure calculation. The electronic coupling divided by lambda is smaller than 1. And this is sort of a necessary criterion for localized carriers. Now let's have a look what's happening in high mobility, what I call high mobility compounds like pentacene. So if you do the simulation for pentacene, you get a completely different picture. So this is what you get from pentacene. You start again from a initial state that's highly localized, and this is not an eigenstate of the system. This is a linear combination of many states. And after some relaxation period, that's usually 100, 200 femtoseconds, you get these structures here forming, okay? And this here, this is what I call sort of the polaron. Most of the time in that crystal, this hole has sort of this shape here, okay? And so this is not a coincidence, because this is actually the T1 direction of pentacene. This is the direction where the electronic coupling is the largest. But still, you see that this polaron is delocalized over roughly 10 to 15 molecules, but not over more molecules. And the reason is precisely you have this disorder. You have the disorder in the electronic couplings that basically destroys these strongly delocalized states. They are strongly delocalized states, but they are thermally not accessible in this system. Again here, so the polaron here is much larger than here, and this, again, the reason is that the electronic coupling here ratio with respect to the revolutionization energy is larger than 1. Okay, if we look at this process in more detail, this is sort of plotted here in that graph, where I plot the inverse participation ratio. Now, luckily that has been defined in previous talks, so this is nothing else than the number of molecules this hole is delocalized over as a function of simulation time in picoseconds. So what you see that most of the time, the IPR is something between 1 and 2, and this is this sort of a localized state that we have seen, and this is that's the time average. But every now and then you see states where the polaron is sort of delocalized over for very, very, very short periods of time, over let's say up to 10 molecules, and so.
Did you implicitly choose a temperature?
This is only room temperature, yeah.
It's room temperature.
So if you think in terms of energy levels, so this would be the top of the valence band, its whole transfer. So these states would be at the top of the valence band, and these states here, the more delocalized one, are sort of somewhere close in the middle of the valence band. Now this is what you would basically what we know what's happening. I mean the states at the top, they tend to be localized. The ones in the middle, they tend to be more delocalized, and the one that at much higher energy again become more localized. Okay? But the ones at at very high energy are thermally not accessible. Okay, so these are thermally accessible, and so it's this kind of dynamics within that valence band that then causes the charge carrier, and this is exactly the same trajectory, but instead of IPI I show here the displacement, causes the hole to displace along the lattice. Okay, and this is the hopping. So with each hop, the charge carrier moves on by a small amount, just 0.3 to 0.5 nanometers, which is roughly the distance between two molecules. Now, again, the situation in pentacene, where it forms this very large polaron, is different. So you see here that already the states close to the ground state are more delocalized, and on average the polaron size is 18, and this is in very good agreement with electron spin resonance data, which were also interpreted that the charge is delocalized over between 10 and 20 molecules. Also, so you can see that this is a highly dynamic propagation in time. So you see that the fluctuation in this IPR are very large, and so these fluctuations to highly delocalized states here correspond to a large displacement of the polaron along this T1 direction. That's the high mobility direction. So some of these things are successful. Then you have the jump. Some of the things are not successful, and then the polaron basically sort of expands, but then shrinks back to where it originally was. And what is also very interesting is the time scale on which these jumps here are happening. So the polarons around 18 is stable on that time scale, which is roughly 200-300 femtoseconds. This is basically what the people using transient localization theory as the tau. Okay, here it's nice because we get this tau, the values for the tau directly from simulation. And in our picture, I wouldn't call the mechanisms of, let's say, transient localization theory. I would rather call it transient delocalization, because most of the time it is actually sort of stably folds a polaron of about 18, and every now and then it sort of expands and then jumps over relatively large distances of 3 to 5 nanometers. This is the big difference. This is why this is a low mobility and this is a high mobility compound, because the polaron is much higher and the jumps are on the order of magnitude of the polaron itself. Okay, so there's no reason why you should believe me now, all the things that I'm saying. Of course, we would like to compare to experiment, and the best thing is, of course, to compare the computed mobilities to the experimental ones. So how do I get, so this is stochastic dynamics, so one trajectory doesn't tell me anything. What I have to do, I have to repeat these things with different initial conditions, and then I have to average over thousands of trajectories. Okay, this is what you have to do here. You have to average the mean square displacement of that carrier wave function in time, and then plot it as a function of time and see how it looks like. And what we see typically is that at the beginning, the first 200 femtoseconds, so you have some kind of relaxation process going on. And this is exactly basically where the whole starts from a localized object to the final polaron size. This is where it expands. This is not Einstein diffusion. This is real sort of quantum mechanics. But then after that process has finished, then the real diffusion process is happening. And this diffusion process here is always in all of the substances that we're looking at linear, so it's indicative of Einstein diffusion. So this delocalized polaron moves in that material with an MSD that goes linearly this time. Now, from this, of course, it's easy to get the diffusion constant and the charge mobility, and then we plot it against experiments. So you see, so the agreement here, so this is our dynamics, all in blue, so the agreement is extremely good. I mean, the problem here is, of course, that some of the experimental values also have pretty large error bars. So for pentacene in particular, you have values between, let's say, 5, right, and 30 in the literature. So okay, so we go usually somewhere in the middle. I should have put some error bars. So for some of the experimental values, we have pretty large error bars. But on average, you can see that the trend is pretty good. So we can couple with this method two pretty different regimes: the hopping regime here on one hand, and then the sort of large polaron regime on the other hand. Okay, so this is not easy to do with this sort of standard theory. Even transient localization usually is good here and here, but maybe not so good here. Now then, of course, is the question: how do the traditional methods do? How does the hopping model do? Well, in green, you have the hopping model, and you can see. So this is side-to-side hopping, green, right? So this model is justified here. So here is fine, and it sort of coincides pretty well with our method. In that regime here, as you can see here, the actual dynamics has absolutely nothing to do with side-to-side hopping. Nonetheless, the mobility that you get with the hopping model is pretty good actually compared to our model and compared to experiment. So why that is, I don't know, but this is actually the reason why the community for the last 10, 15 years always got away with these hopping models, okay? Because the mobilities that actually came out from this was actually pretty good, even though the mechanism had nothing to do with that. Okay? Now, also you might wonder, where is band theory for these compounds? So this is where band theory is. Okay, so this is sort of expected. It doesn't do a very good job for these compounds. It only becomes better here in the sort of very high mobility area. Okay, so then the plot that people always say, this is obvious. Okay, maybe it is obvious. I'm still showing that plot. So this is inverse participation ratio, number of molecules, the the excess carrier is delocalized versus mobility. So you see, okay, so this is mobility increases, IPR increases. Okay, not a big surprise here again. For pentacene, we match the value from electron spin resonance pretty well. I mean, this sort of X in the green is certainly a bit fortuitous, but I mean, it is an indication that we are doing the right thing. Okay, so this combined with the mobilities. And again, I mean, so what we see is that this polaron size is up to roughly 20 molecules at room. That's all at room temperature. Now, how does transient localization theory do? Well, the honest comparison would be looking at the red data points. Now, the red data points, this is transient localization theory from Frattini and Giucci. Okay, so these are our mobilities. Perfect agreement with experiment is on that black line here. So this is a factor of 2. So you see. The way how we generated this data is that we used exactly the same electronic Hamiltonian that we used for the blue data. We basically put into the TOT theory. Okay, then you get this. So you get the trend is pretty good. It's very good. You have a slight underestimation of the absolute mobility values. Interestingly, if you remove the diagonal electron-phonon coupling, then you get the green data, and then you're almost there where we are, but this is sort of inconsistent because we actually have the diagonal electron-phonon coupling in our simulation. Okay, but this is just to say that the qualitative trends between these two different approaches to charge carrier mobility give sort of comparable results, let's say. Okay, so the summary. So I think if you think of excess charge carriers in organic materials, in highly disordered small molecule organic materials, this is the kind of, I think, picture that comes out of our simulation, and we believe is the right one. Okay, so here from low mobility to high mobility, so these are the related pictures. Now we have to zoom out for the high mobility ones, obviously. Becoming larger and larger, we have to zoom out. And so we also see nicely the correlation here. That's the mobility now angle resolved. Okay, so the direction of the mobility tensor essentially also nicely aligns actually with the extension of the direction of the extension of the polaron. Okay, just for explanation, because it's really very small. Each one of these black objects here is a pentacene molecule. Okay, so it's really large, right? It's not a single molecule, so it's large, and it's large because the eigenstates of that electronic Hamiltonian are delocalized. Okay, especially the eigenstates that are thermally accessible at 300 Kelvin. So that's the reason. But it's not a band because all these electronic couplings, they have a static disorder, and that breaks basically this band-like electronic states. Okay, so that's the reason. And then in terms of transport mechanism, I think what comes out of our calculation is a diffusive jump of that polaron. And for the small mobility and for the high mobility material, right? Small mobility just localized over a single moiety, and for high mobility, you see polaron here. This is the normal state. It's same 20 molecules. A certain instant of time it expands, delocalizes. It's almost twice its size, and then after a couple of vibrations, then it sort of collapses to its original size. And this collapse, it can either be successful or unsuccessful. If it's unsuccessful, it stays where it was. If it's successful, it moves another 5 nanometers along the crystal. Okay. So let me now quickly also come to the, I don't know how much time I still have.
About 10 minutes.
Great, thank you. Okay, so this is now a sort of second application of the methodology, alkylated tetracene stacks. So we were interested in this because, well, I think it's of interest to sort of design better 1D stacking materials. I mean, the classic one is hexabenzochronomine, but interestingly, I think the measured mobility for that is just 1 square centimeter per volt in second. We looked at this because there people in Japan have actually synthesized tetrazine, promisingly looking tetrazine derivatives, and they have also deposited crystal structures, and this is what we need for our simulations. We are not doing crystal structure prediction. We need like crystal structures. So now then Orestes did non-adiabatic dynamic simulation of whole transport in all of these tetrazine derivatives with R varying. So these are sort of methyl side chains of varying size. So what you can do, I mean, you don't have to start with, let's say, if you want to screen this data base for high mobility materials, you don't have to do the non-adiabatic dynamics and all this stuff. So at the beginning, it's sufficient to just calculate these charge transfer parameters, so the electronic couplings and the reionization or trapping energy, and that already tells you a lot whether this is a good or a bad conductor. And the threshold is this psi. I don't know whether you still remember. So this is twice the coupling over reionization energy. Now, if this is 1, then you're sort of at the threshold between small polaron and delocalized polaron transport. So for a compound to have to be a pretty sort of have delocalized polarons, this thing here should really be sort of above that peak line. Okay. And what you can see in all of these compounds, there's at least one coupling direction where you're basically that's bigger than this. There's only one compound here. This is the tetraethyl. So each of these things here is substituted by an ethyl group, and it doesn't have a single coupling that's above the threshold. So you would already sort of from this already expect that all of them are pretty good except this one. And if you do the non-adiabatic dynamics, then this is exactly what you see. So, well, what I say bad here is just 2, right? But it's bad compared to the other ones that we predict here. So we predict that this one actually has 5 or 5.5 square centimeters. And what you actually see here is a correlation, again, between the IPR, the delocalization of the polaron, and the mobility. And then here you see very nice sort of linear correlation. Okay, so these are sort of the extreme ones. So this is the one that forms that is low mobility. So you see the delocalization is just 2 molecules. So this is a coarse grain presentation. So this is basically how it moves from one place to the other. And then the other one is this. So you see this is more delocalized polaron and moves quicker from left to right. Again, here you can see the difference in that psi value here. Okay, what is maybe striking in terms of rational design of these materials is that the difference between these 2 molecules is just one CH2 group, right? It's really not much. It's just here you have ethyl and here you have methyl. Small difference in chemistry, but you're basically at the opposite side of that spectrum. The reason is clear why that is. And that has exactly to do with that orbital overlap that already Henning Searinghouse was talking about in one of his slides. Now look at this. This is the stacking of these materials along that high mobility region. In the tetramethyl, which is a lousy conductor, not a very good conductor here, you see that, and here are the homos. This is the homo of one molecule, and this is the homo of the other molecule. So if you compute the overlap between these 2 orbitals, so you always see that the plus of one molecule overlaps with the plus and minus of the other molecule. Okay, Now, if you integrate these kind of phase combinations, then you get nothing, zero. You get zero overlap, you get zero coupling, very small coupling, and therefore a small mobility. Now, on the methyl, so just one CH2 less, the stacking is just slightly different here, but different enough that you go from a destructive to a constructive orbital overlap here. So you nicely see here, you have plus plus, minus minus, plus plus, minus minus. That gives a large overlap and large coupling. So that's basically why these two things are at opposite side of the spectrum. So now you can also see that it will be quite difficult actually to sort of like go from one derivative to the other, for instance, to minimize the coupling fluctuations that I'm not really talking about here, because what you will invariably also affect is actually the mean value of the couplings. Okay, so this is what I quickly also want to just finish with is, okay, so we are very often talking about design rules. So what really needs to be the case so that I get large mobility values? Well, the first one is that the most crucial one is, of course, that you have delocalized charge carriers. Not. And when do I have this? This I have once the expectation of electronic coupling at a given temperature is larger than 1.5. Okay.
Is that with A and B unequal adjacent?
Sorry. Yeah, these are mixed neighbor couplings. Yeah. Okay, so then you have these delocalized objects. How delocalized they are, then that depends on a number of other issues. Then what we heard from Hennig's talk, what is very important is the thermal fluctuations of the electronic coupling. That should be as small as possible, and it should be as small as possible so that the site energies, and this is clear. I mean, what you want is that the difference in the diagonals between two different sites should be within the energy that couples these two diagonals. Obviously, then you get this is what I call resonance. And this is something that people don't talk much about, but there is also a site energy and the site energy fluctuation. That should also be very small. Okay? So these things should be, would guarantee that you have high mobilities. And how can I achieve this? So for one, you obviously need good stacking, constructive orbital overlap, small realization energy. For two, little thermal motion around the lattice site, locked structures. And again, for three, since these fluctuations are proportional to the reorganization energy, so the organization energy should be small. Now, Frattini in his paper now, he has additional rules, and I would say that these are modifications of Rule 1, so he refined these. So what he says is for 2D materials, what you should have is isotropic coupling, so it's bad to have only high coupling in one direction and not high in the other, so it's better to have half of the coupling in one direction and half in the other, so isotropic is the preferred one. And then there is also sort of a more subtle rule that has to do with the correct sign combination of the couplings in different directions. And all these arguments, basically, they have the aim to create strongly delocalized states at the ground state or sort of thermally accessible electronic states. Okay, so that's the ultimate aim. Okay, so we looked at this very quickly. Looking at these organic crystals that we have studied before, and we did an in silico experiment, if you like. So this is the nice thing that you can do on the computer, not so easy to do, unfortunately, an experiment, is that we just froze all the off-diagonal electron-phonon couplings, and we set the off-diagonal electron-phonon couplings to the mean value, and there is no fluctuation. And this is the result. So what you see is actually that the mobility in the low mobility region, the mobility actually decreases if you remove those fluctuations. And this is actually expected because here, this you can describe with Marcus theory, hopping theory, and this is proportional to AJB square bracket. and AJB square bracket is AJB bracket square plus sigma square. So if you reduce sigma square, we set it to 0, then of course then you also reduce the prefect of the rate, therefore you have a small decrease. But this is not the important part. The important part is here in the large polaron region. So here you predict if you really could freeze those things, then you get sort of a major boost in mobility, again predicted by our non-adiabatic MD simulation, especially for let's say rubrane and tensor that can be up to a factor of 7. But of course, this is not possible. At least it's not possible to remove all of it of the I don't know, electron-phonon coupling. And that comes me to the conclusion. I hope I still have half a minute. So we have developed a non-adiabatic MD method for real-time propagation of charge carriers in soft materials, and it's not probably the best possible you can do in terms of theory, but it's probably the best possible that you can do for these kind of materials. So it's efficient enough so that we can actually look at sort of application relevant systems. We can simulate up to 1,000 molecules that would correspond in a DFT calculation to 100,000 electrons. So you can do this nowadays with DFT, but maybe just one electronic structure calculation probably takes a couple of months or something like that. And the nice thing is also it's a stochastic methodology, so we have to run lots of realizations, and we can actually converge. I didn't show this, but we can converge our results very well in terms of trajectories. The experimental mobilities that are available, I think we could reproduce them very well, usually within a factor of 2, which is, I think, pretty good, but there is also, of course, some uncertainty in the experiments. And I think with that, I think sort of a new picture of charge carriers in soft materials sort of emerges. It's not hopping, it's not band, it's sort of the transport of a sort of hole or electron that's delocalized over maybe up to 20, 30 molecules. And what I also want to say is that our numerical simulations, I think they provide benchmarks for beautiful theories, like transient localization theory, or also for stochastic reveal, for instance. And I think it's useful. It's not, you cannot use this to do large-scale screening of 10,000 molecules or something like this. For this, it's sufficient to just calculate the electron transfer parameter, H of B lambda, and then once you have maybe 10, 20 candidates, I think then our methodology, I think, can be used to predict charge mobilities. With this, well, there's also an outlook. So basically what we would like to do is to apply this now to interesting processes also at interfaces, including charge combination, the things that Jenny talked about, and also a little bit more theory here beyond surface hopping. So there's a nice, better quantum dynamics methodology that we are currently developing. That's my group. So that was really a group effort. Antoine had major contributions here, and also Samuele, of course, who is here in the audience. Also Matt for making these nice movies, and also Orestes for his work on tetracene. Orestes is also here. And finally, some advertisement of our international workshop on organic materials, which will take place at University College London, 17th to 19th of June. We have a pretty good lineup of speakers, including the chair of this session, and also Henning Serienhaus, and then a couple of other people who are pretty good at computing things, and lots of also very interesting invited speakers. So I hope that many of you will sign up for this exciting event next June. Thank you for your attention.